All right, what's the next question? So consider the following function subl that computes the list of sublists of a given list. Okay, here's some big yucky definition, where we've got some other definitions. Show using structural induction that length subs, I think that should be subl. There is no subs. Okay, for all list L of type A. Here we assume the standard definition of length function, cool. And we also have the following properties, that if you map a function, that doesn't change the length of a list, and the length of xs concat ys is length of the first with length of the second. So we can use these two rules for free. I can't really fit both things here, so I would recommend while you're watching this video, keep this piece of paper handy next to you, because I'm not going to look at it ever again. Whoopsies, that's the wrong piece of paper. Here we go. Okay, so what have we proven? We've proven length of sub L is 2 to the length L for all lists L. So state and prove the base case. Okay, so here's what the base case is. The base case is the thing we wanted to prove, but L is empty. So our base case is length of subl empty equals 2 to the length of empty. Okay, and here's the proof. So the left-hand side of this is going to be length of list containing empty list by rule S1. So length of list containing empty list, L1. Well, what's list containing empty list can also be written as empty list cons empty list. That's just what it means to have the singleton list containing an empty list. So this is that, I don't know, by Haskell syntax. And then length of something cons onto something is 1 plus the length of what's left over. 1 plus length of empty by rule L2, which is 1 plus 0 by rule L1, which is 1 by math. Okay, left-hand side is 1. So what's the right-hand side? So the right-hand side is 2 to the length of the empty list, which is 2 to the 0 by rule L1, which is 1 by math. Cool, we got 1 on both sides, therefore left-hand side equals right-hand side. Alright, so far so good. State the inductive hypothesis. I mean, that's just the thing that we want to prove, right? So, length subl L equals 2 to the length L. And this is not for all L, this is just for like we fix some L and then we use the same L in the step case. We're not going to worry about quantifiers of other variables because there ain't no other variables. Alright, now state and prove the step case. Okay, so what's the step case? Step case is for any new element X bolted onto the front of the list L, the property is still true. So we need to prove for all X, length of subl X cons L is 2 to the length X cons L. Okay, so I guess we'll let X be arbitrary and then proceed with the proof. So the left-hand side is length subl X cons L. Subl X cons L turns into all this rubbish, so I guess we'll just do that. So we got length of all of that crap. So subl L concatenated map, Lord knows whatever the pref function does, doesn't matter. Pref X subl L by rule S2. And length of two things concatenated together is the same as the length of the first thing plus the length of the second thing by LA. So I'm going to apply that rule. So length subl L plus length of all this junk. Length map pref X subl L by rule LA. Length of something mapped is length of the list unchanged by LM. So that means length of map blah subl is the same as length subl. So we have length subl L plus length sub L. By rule LM. Well, these are the same things, right? So this is just 2 times the length of sub L by math. And then now this term here matches my inductive hypothesis. This is 2 times 2 to the length L by inductive hypothesis. 2 times 2 to the blah is 2 to the 1 plus blah. So that's going to be 2 to the 1 plus length L by, like, that's how, like, exponentiation works, so by math. And the 1 plus length L is the same as length x cons L. So 2 to the length x cons L by math. No. By the definition of length by L2. Which is what I wanted, which is the right hand side. Cool. Proof is complete.